welcome to today's lecture. So we're going to start sequences. Sequences and series are one of the most important topics in calculus. You see a lot of applications of sequences and series in different branches of science. Well, I'm going to write down the difference between these two first. Then we're going to go over the details for both of them, over the definitions, the theorems. So the difference between sequences and series is that when you have a sequence, you list the terms of a sequence. When you have a series, you add the terms of the sequence. So a sequence is denoted by the terms like this. You write down the first term, a sub 1, comma. The second term, a sub 2, comma. The third term, a sub 3, comma, the rest of them. So first term, first y value, second term, second y value, the third term, the third y value, and so on. So we separate these by commas. When it comes to a series, we add the terms of the sequence. So we add.
Professor, I think it needs to be manually focused again.
So we add the terms of a sequence and we define a series. So the terms a sub 1 plus, so plus a sub 2 plus a sub 3 plus the rest of them. That's the main difference between a sequence and a series. So for a sequence, you just list the terms. For a series, you add the terms, summation, addition. Okay, now we're going to officially define a sequence and try to analyze a sequence. Then we move on to series. Note that when we're dealing with sequences, we need the limit of functions. When we study sequences, we need the limit, what you learned in elementary calculus, limit of functions. So if you need to review the limit of the functions, you can find some limit definitions on Canvas. Please review those. And if you have access to some supplemental videos, please watch those. A sequence. Definition of a sequence. A sequence is a function. A sequence is a function. Remember that when you're dealing with a function, you need to have the domain of the function. Is a function defined on n. What is n? N is natural number set. We denote this with f of n that maps the element of n into R. Or denote it this way. You say that, hey, A sub n maps elements from n into R. So n is the natural number set, and R is the real number set. And counting numbers starts from 1, 2, 3, 4, and so on, natural numbers. And R, bolded R, is real numbers. Perfect. So a sequence like f of n is a function that takes some values from n and map them to R. It's denoted by a sub n as well. So you can write it this way. F of n equals to a sub n. Sometimes we denote it this way. We use curly brackets and write the general term inside the curly bracket. These are all notation for a sequence. N is equal to 1. We get the first term of the sequence a sub 1, f of 1, a sub 1. So this is your first term. You can say that, hey, this is my y value. If n is equal to 2, you get f of 2 or a sub 2, which is the second term, or another y value. Then n is equal to 3, we get f of 3, a sub 3, the third term. Another y value for you, and you continue this process. These are the terms of your sequence. Some examples. Examples of sequences. First example that we're going to talk about is f of n equals to n over 1 plus n. So we have a function. This is definitely a function. This function f of n is defined from n to R. It means that it takes some values from n, 1, 2, 3, 4. If you don't have any restriction on the domain, you always assume that it starts from 1. So let's follow some steps. Step 1, find some of the terms of this sequence. Find some terms of this sequence. So n is equal to 1. It means that f of 1 is 1 over 1 plus 1 or a half. Next term, so this is your first y value. This is y value. N is equal to 2. You get f of 2, which is 2 divided by 1 plus 2, or 2. This is your second y value. So see, we're just plugging x values, n values, and then we find the y values. N is equal to 3. You get f of 3, which is equal to 3 over 1 plus 3, which is 3 over 4, another y value. Well, you continue this process. This is your step 1. Step 2, graph this. Graph these terms. To understand the general behavior of your sequence. Okay, here you have your n, On the horizontal axis, instead of x, you have n, and on the vertical axis, you have f of n. Well, okay, here you have n equals to 1. Our y value is a half. 1 and a half. This line continues, guys. N goes to infinity. And here you have 1. Okay, our first y value is a half. When n is equal to 1, we have a half. This is our first dot. Our second dot, 2/3. A little bit further on here. This is your second dot. Not far away. Then we have our third dot. It's very close to this guy. And then our fourth dot, and here we go. Third dot, the fourth dot, and it continues. Step 3. Find the limit of f of x. F of x. So, why we are finding the limit of f of x? When x goes to infinity, n goes to infinity, the behavior of these two functions are the same. At infinity, they have the same behavior. So the limit of f of n while n goes to infinity is the same as the limit of f of x while x goes to infinity, which is the limit of x divided by 1 plus x while x goes to infinity, which is equal to 1. So when x n goes to infinity, the limit of our sequence is recall that in elementary calculus we learned about the limit. So this is a recall for you. If you have limit of, for example, f of x divided by g of x while x goes to a, and this is equal to 0 over 0, or if you're taking the limit and it is infinity over infinity, then we apply L'Hopital's rule and we say that, hey, this limit is equivalent to the limit of the derivative of f divided by the derivative of g while x goes to a. And if this guy again is 0 over 0 or infinity over infinity, you continue this process by taking the second derivatives. You find the limit of the second derivatives. And again, if this guy is 0 over 0 or infinity over infinity, L'Hopital's rule says continue this process. Continue taking the derivative until one of the numerators or denominators is not 0 or infinity. So take a look at this case. If x goes to infinity, you get infinity over infinity. So L'Hopital's rule says that this is equivalent by taking the limit of the derivative of x, which is 1, divided by the derivative of 1 plus x, which is 1, or equals to 1. of f of x in Desmos. So here we have our graph. So we are using Desmos to graph x divided by 1 plus x, and see the difference between the graph of your function when it has x, the domain is r minus -1, and the graph of your sequence. So this is the graph of our sequence. This is the graph of f of n equals to n over 1 plus n. And the graph of f of x, which is x over 1 plus x, is graph of a reciprocal function which behaves like this. Well, the graph is continuous, and because of vertical asymptote, it has 2 parts. So the graph of f of x, the graph of f of n. Graph of f of n has gaps in it. You're not allowed to connect these. You must have gaps. Gap, gap. This is discontinuous. This is discrete. This is the topic that we are discussing in discrete math. The graphs of functions that has gap in them. There is no gap. No gap. Just connect all of these dots because x belongs to R. You're allowed to plug in x equals to 1, x equals to half, x equals to square root of 2. You're allowed to fill in the gaps. And note that x can be negative, x can be positive. Here n belongs to, n is in n, counting numbers. Counting numbers is not negative. It starts from 1, 2, 3, 4, and so on. Here x is in R minus 1. So there's a difference between the graphs of a sequence and the graph of a function with different domains, but note that at infinity, when x goes to infinity, when n goes to infinity, the n behavior are the same. More examples for you. This was our first example, and we have other sequences. These sequences. Let me list some of them for you here. This is A, B, another sequence for you. For example, f of n equals to -1 to the n times n plus 1 divided by 3 to the n. You can define another sequence using g instead of f. It's just a function. You get square root of n minus 3, and n must be greater than equals to 3. And then another one, d, h of n, which is a trig function, our favorite topic, cosine pi n divided by 6. And here we go, and it's pi greater than equal to 0. We can plug in, for example, 0 here as well. So these are examples of sequences, different sequences. You're allowed to use any function notation that you use, like square root, the fourth root, the third root, trig functions, and so on. We are interested in finding the limit of these sequences while n goes to infinity. What is the limit? What is the limit here? Again, if you are hazy in taking the limit, please review elementary calculus. Please go over the notes, the supplemental videos. It helps you to refresh your memory and prepare for the rest of the course. So we're going to review the limit of sequences, define different sequences, and we're interested in the end behavior where n goes to infinity. Another example for you. In this example, question says, hey, find the limit of n over 1 plus n while n goes to infinity. And after this, we're going to go over another examples involving the ln. Okay, we want to find the limit of this sequence, and we saw that the limit of this sequence is equivalent to the limit of f of x while x goes to infinity, which is the limit of x over 1 plus x, x goes to infinity. And by using Hopital rule, you can say that, hey, this is infinity over infinity, and the limit is equal to 1. Another example. Find the limit of ln of n divided by n while n goes to infinity. Okay, let us follow the steps that we have. Step 1, find some terms. So here you have an for f of n equals to ln of n divided by n is equal to 1, a sub 1, or f of 1, they are the same, is equal to ln of 1 divided by 1, 0 over 1, or 0. N is equal to 2. You have to use a calculator. A sub 2 is equal to ln of 2 divided by 2. Calculator. N is equal to 3. A sub 3 is ln of 3 divided by 3. Use a calculator. And find some terms. Step 2, graph it. And step 3, eventually we want to find the limit of this function. And let me write step 3 here for you. Limit of ln of x divided by x while x goes to infinity, which is equivalent to the limit of your sequence while n goes to infinity. We call that an and fn. They are the same meaning, the same notation, the same symbols for sequences. So this is the graph of our sequence. By finding n equals to 1, your y value is 0. N is equal to 2, your y value is 0.34. N is equal to 3, your y value is 0.36, and so on. So as you can see, there are gaps in between these points. You're not allowed to connect these points. It's not a continuous function. Now, to find the limit of your sequence, you can take the limit of the function that you learned in elementary calculus, ln of x divided by x. while x goes to infinity and n goes to infinity, the end behavior of these two functions, the y values at infinity behave the same. So the limit of ln of x divided by x while x goes to infinity is equal to infinity over infinity. So L'Hopital's rule says, hey, take the derivative of ln divided by the derivative of x. The derivative of ln of x divided by the derivative of x while x goes to infinity. This is limit of 1 over x divided by the derivative of x is equal to 1 and x goes to infinity. This is equal to the limit of 1 over x, x goes to infinity, 1 over infinity is equal to 0. So the limit of ln of n over n, while n approaches infinity and n is very large, is equal to 0. Okay, awesome. Another example. So question says, what's the limit of negative 1 to the n divided by n while n goes to infinity? Let us follow some steps. Step 1, let us write down some of the terms. N is equal to 1. We get negative 1 to the first power divided by 1, negative 1 over 1 or negative. This is our first y value. N is equal to 2, negative 1 squared divided by 2, a half. N is equal to 3, negative 1 to the third divided by 3, negative a third. N is equal to 4. You get negative 1 to the fourth divided by 4, a fourth, and so on. Let's graph it. Step 2. Graph the sequence, see how it behaves. Again, we have n, and we have function like f of n, an, it doesn't matter, an equals to f of n equals to negative 1 to the n over n. Okay, perfect. N is equal to 1. Well, I have a negative y value. 1, 2, 3, 4, 5, 1, and negative. So the very first point is 1 and negative 1. First dot. The second dot is 2.5. 2.5. Then we have 3, which is negative a third. Okay, I'm getting closer and closer to horizontal line. Then I have 4, a fourth, and so on. So this is going to be here, 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 and the rest of the ones. Again, we are not allowed to connect these. You're not allowed to connect these. You should have gaps. This is discontinuous graph. Gap, gap everywhere. There are gaps. Okay, perfect. Step 3. Find the limit of f of x when x goes to infinity, which is the limit of negative 1 to the x divided by x when x goes to infinity. You get a number divided by infinity, which is equal to 0. Okay, by analyzing the behavior of f of x, I know at infinity the limit of my sequence is equal to 0. Limit of negative 1 to the n over n when n goes to infinity is equal to 0. Just a recall for you. And here you have actually a theorem. Recall that the limit of 1 over n while n goes to infinity is equal to 0. 1 over infinity is equal to 0. So what's the relation between 1 over n and negative 1 to the power n? 1 over n is actually the absolute value of negative 1 to the n over n. N is positive, so the denominator stays the same. The absolute value of negative 1 is always positive. So the theorem says if the limit of absolute value of an while n goes to infinity is equal to 0, then you're allowed to have this conclusion that the limit of an while n goes to infinity is also 0. Nice theorem for you.